this video, you will be introduced to the concepts of reproducibility and replicability, and why they are important in the context of data science projects. First, let's start with a couple definitions. Reproducibility is defined as obtaining computational results using the same input data, computational steps, methods, code, and conditions of analysis. Whereas replicability is obtaining consistent results across studies aimed at answering the same scientific question, each of which has obtained its own data. So one way to think about the difference between reproducibility and replicability is reproducibility is when you use those same methods or procedures with the same data and code used in the project to see if you can get the same results. Whereas with replicability, that is where you use the same procedures, but you go out and collect new data and potentially write new code to test the hypothesis or research question and see if you get the same results. Robert Pang suggested the idea there is a spectrum of reproducibility and replicability. At the far end is the traditional model of publishing, where you simply release an article publication, which is not really reproducible. If I actually wanted to see if I could reproduce a colleague's findings, at a minimum, I would need access to their data and code. Farther down the spectrum, I would need the code and data in a linked and executable computing environment. And then at the far end of the spectrum is full replication, where you collect new data and code to test the hypothesis. So why is this important? There have been numerous studies over the past decade that have found that scientific findings are not as reproducible or replicable as we would like, which has led some to saying science has a reproducibility crisis. So for instance, a Nature survey published in 2016 asked scientists if they thought there was a crisis, and around 90% indicated they thought there was either a significant or a slight crisis. Even more notable were the high number of scientists that indicated they had failed to reproduce either their own or someone else's results. Making this even more complex is the idea of reproducing findings as time progresses. Another interesting Nature article proposed a challenge to researchers to see if they could get their 10-year-old code to run. Some researchers got very creative, but they found significant challenges because they didn't have full documentation, had a hard time tracking down the hardware and software, or entire computational environments had become obsolete. As we consider developing more reproducible workflows and building a culture that values reproducibility, there are many factors that can impact success. At the foundation are the technical factors, including the tools we use and our scientific workflows. Then there is the human element of generating buy-in with a research team and how we incentivize doing this work in the already busy and competitive culture of academia. There's no easy solution to approaching reproducibility, but some, like Lenny Tettleman, are suggesting we reframe this issue and look at it not as a crisis, but as an opportunity to work together to advance the scientific endeavor. As new tools and approaches are developed and skills are gained, we can lay a firm foundation for realizing more computational reproducibility going forward.